Howdy, I'm Farida,
And I'm Anissa.
and today we're going to be showing you how to plot a Bode plot of a bandpass filter. A bandpass filter is a device which passes frequencies within a certain range and rejects frequencies outside of that range. And a Bode plot is just a visual representation of what a filter can do. It is a graph of the frequency response of a system.
So, how do you draw a Bode plot? You do that using the transfer function which you derive from your circuit. So, this is an example of what a transfer function could look like. Up front, you have the constant, in the numerator, you have something called zeros. In the very front, you have a zero at the origin. And here, you have a zero at frequency WN1. In the denominator, you have poles. Similar to the zeros, you have a pole at the origin and another pole at frequency WN2. Now, if you don't know what this means right now, don't worry about it because we're going to explain that later. The whole idea of this transfer function is that when you solve your circuit, your transfer function might not look exactly like this, but you can easily rearrange it to get it in a similar form. This will make drawing your Bode plot a lot easier. Using this table, we are going to explain how every part of a transfer function affects a Bode plot. First, we're going to start with a constant. The constant will always have a line with a gradient of 0, and its magnitude will always be 20 log to the base 10 of the constant. This is because we want to convert the constant from volts to decibels. The reason that we're doing this is because in a Bode plot, the y-axis is magnitude in decibels, and the x-axis is frequency in decades, which is a logarithmic scale. Therefore, we can't plot the constant in volts, it has to be in decibels. We have two different kinds of zeros, the zero at the origin and the zero at frequency WN1. For the zero at the origin, it has a gradient of plus 20 decibels per decade and passes through the 0 decibel point at frequency 1. For the zero at WN1, it will have a magnitude and gradient of 0 if the frequency is less than WN1. If it's more than WN1, it will have a gradient of plus 20 decibels per decade. We also have two different types of poles, the pole at the origin and the pole at frequency WN2. Poles and zeros are very similar. The only difference is that poles will always have a negative gradient. So the pole at the origin will have a gradient of negative 20 decibels per decade and will pass through the point 0 decibels at a frequency of 1. For the pole at WN2, if the frequency is less than WN2, it would have a magnitude and a gradient of 0. But if it's more or equal to WN2, it will have a gradient of negative 20 decibels per decade. Now, if you can't visualize what the Bode plot looks like just from using this table, I completely understand. And that's why my friend Anissa is going to solve a transfer function and help you plot a Bode plot.
So here we have an example of our transfer function that could be derived from any circuit. So in order to get it as close as we can to the slide that was shown at the beginning, to our Bode plot form, we're going to have to do some factoring. So let's go ahead and do that. We're going to go ahead and factor out 100 from the numerator. So we get 100 times s plus 1. And on the bottom, we're going to factor this out, which comes out to s plus 10 and s plus 100. Now, we can see that it's starting to come into place as our original transfer function, but now we have to do a little bit of extra work. So we're going to have to divide each parenthesis by the frequency that's being added. And on the bottom, we have to factor this 10 and this 100 out. So it comes out to 10 times 100 times s over 10 plus 1 times s over 100 plus 1. So now that we've gotten our transfer function as close to the form as we explained earlier in the video, we can now see that these constants here are equal to our value of k. In the numerator, we have a 0 at frequency Wn1 equal to 1, and then we have two poles present, one at Wn2 equal to 10, and another one at Wn3 equal to 100. So here we see that our constant is actually in volts. So we're going to do that conversion that we showed earlier to convert this to decibels. So we're just going to go and plug this in as 20 log base 10 of, these will end up canceling, so we're just going to be left with 1/10, which this comes out to be -20 decibels. So here we see just the regular axes for a Bode plot. So here we have our logarithmic scale in radians per second, starting at 10 to the -1, going by factors of 10 all the way to 10 to the 4th. And on the y-axis we have in decibels, went ahead and put 0 about center, and then we went down -20 decibels all the way to -40, and then up in the same direction. So now we're going to go ahead and start plotting our different lines. And we're going to start first with our constant. So as we recalled previously, our constant has a slope of 0, and we found what the magnitude of that is. So we're going to go from -20, and we're going to draw a slope of 0 line all the way across our Bode plot. Next, we're going to go ahead and draw our 0. So we recall from previously, 0's rise at a rate of 20 decibels per decade at Wn equal to 1. So this is Wn equal to 1 right here. So we're going to go starting at 0, we're going to draw our dashed line up into this point. Then we're going to rise at 20 decibels per decade. So we're just going to follow this up and just plot a point. And then we're going to do our dashed line. Oops. Right here. That's our 0. Now for our poles. These are going to drop at a rate of 20 decibels per decade at both of our cutoff frequencies that we found. So we have one at Wn, which is equal to 10, and another one at 100, which are these values here. So again, we're going to go from 0 all the way here to about this point, and then we have another one about here. So for our first one, it's going to drop at a rate of 20 decibels per decade. So we're going to go and plot a point right here, and it's going to drop. This is our first pole. For our second one, we're going to just keep along our gradient of 0, and then we're going to drop down 20 decibels per decade. That's our second pole. So we went ahead and separated our Bode plot lines by segments into which all the slopes are differing. So for our first segment, we have from 10 to the -1 to 10 to the 0, which there's no slope. So we're going to just go ahead and draw a straight line across the -20. For our second segment, we have it from 10 to the 0 to 10 to the 1, and the only slope we have attributing is our positive 20 decibels per decade rise. So we're going to go ahead and rise up here. For the second segment, between 10 to the 1 and 10 to the 2, we have a positive 20 slope as well as a -20 slope, and when you add those together, we get a slope of 0. So we're just going to go ahead and draw a straight line across here. Now from 10 to the 2 on, we have a -20 slope, a -20, and then a positive 20. So overall, this gives us a -20 slope, and we're just going to go ahead and draw a straight line all the way down. Now this here is a bandpass filter, because we can see that prior to 10 to the 1, we're cutting off any of the frequencies lower than that, and after 10 to the 2, we're cutting off those frequencies, only allowing this band to pass. We hope that you found this video useful, and the method that we showed you throughout can actually be used for various different Bode plots and transfer functions. We hope that this fulfilled your Bode plot needs for the day. Thanks, and Gigo!